Hello everybody, welcome back to the channel. Today we're gonna talk about the various powers and the real power, reactive power, active power, complex power, so on and so forth. So today the math involved is very minimal, but there are a number of the concepts really need to be taken care of. So a little bit confusing maybe. I hope you can rewatch this video a few times in order to understand the concepts. Okay, so let's get started. I'm gonna have two topics. One is the real and reactive power, or the active power and reactive power, and then the second topic is the complex power. This is really built upon on the lecture number 6 when we talk about when we did the power energy analysis for the steady state sinusoidal systems. And so let's start on as kind of a review, and let's start with the things we already had before. So the instantaneous power, by the way, the I have the current I and V labeled for this circuit. This circuit could be anything inside this circuit, with the source or without source, doesn't really matter. And so the instantaneous power delivered to the source, delivered to the circuit instead. The circuit is, we use a lowercase p, pt just equal V times I. And if we substitute this in, we got VA IA times the cosine omega t plus theta v, and plus times cosine omega t plus theta I. And use the trigger identity, we can get the half VAIA cosine the sum, and cosine 2 omega t plus theta v plus theta I, and plus the cosine the difference, which is theta v minus theta I. So these are the things we knew in chapter 6. And if we take the average, we take the average. So the average power, also called the real power, called the real power or active power, and the P is just equal the average one, the instantaneous power, and we know the average, that's going to be only the DC term, right? So the half VA times the IA times the cosine theta v minus theta I. Okay, so this is the real power or reactive power, or the active power, right? And the things we want to introduce a concept of the RMS value rather than carry this to the half all the time. Through the RMS value, RMS means root mean square. The RMS value, let's call the voltage VRMS. We use subscript VRMS. The voltage for the voltage is VRMS is the mean 0 to t the square, and we also need to take the root, and that's VT square dt, and we need to take the root. And if you calculate this, and if you substitute the VT in this, and you will calculate the end result. I'm not going to derive this. The end result is just equal VA over square root 2. This is true for sinusoidal VT. And we have a sinusoidal VT defined as this. And we similarly we can do the RMS for the current. That's equal the root 1 over t 0 to t I t squared dt. And if you carry out this integration and take the root, you will get I sub a, the amplitude, the peak value, or divided by square root 2. This is for sinusoidal. This is really critical. I would put a different color here. This is the only true if this is a sinusoidal. Okay, if not a sinusoidal, you really need to calculate again and see what that RMS value really is for sinusoidal IT. Right. And so if we replace this, and also I want to define the one thing is called the angle. This angle I call this using the phi, and the power factor angle. The power factor angle is phi is equal to theta v minus theta I. And the cosine of phi is the power factor. So there are a few concepts here. The power factor is PF is cosine phi. So in power system, we are talking about the power factor. If power factor is 1, that means phi is equal to 0, right? So if a power factor is equal to 1, that means the current and the voltage in perfectly in phase. So that's the case when the utility company most happy about, because if you're not in phase, we're gonna talk about the reactive power soon, and you actually need to increase the current to deliver the same amount of real power, and that's what they charge you for. And so the power factor PF is so PF is equal to 1. That means the phi is equal to 0, right? So if we define these, and the real power, the P is going to be equal V RMS times I RMS times the cosine phi, or that's equal to V RMS times the I RMS times the power factor, right? So the things now is a little bit more compact, right? Compared, so we don't have to carry this this 2 over this 1 over 2 anymore. So if we use the RMS value, and then we talk about the reactive power. So the reactive power is unlike the reactive power we commonly used Q to denote that. The Q is, we just define that. So let's see, we just define the Q as V RMS I RMS times the sine power factor angle, right? So this one is not a mathematical derived from somewhere. It just define a quantity, and this reactive power in the real world is very useful in terms controlling the voltage in the power system. Is mainly the reactive power playing a big role in that case, and try to maintain the voltage at the very close to nominal value. Let's see at our household we have 120 volts, right? So the voltage is very close to that value all the time. The reason they can do that is because there is the voltage level control by injecting reactive power, so on and so forth, to maintain that. If that voltage level cannot be maintained, the system could have some trouble. Okay, so this, although this reactive power is not real, but it's very important in practical world. Okay, the reactive power also called imaginary power. The reason we will see soon as we talk about the complex power, because that's the imaginary part of that complex power. Okay, and one thing I want to mention that is for the power factor, So if the we will see the power factor leading or lagging. I need to get that concept also introduced. So if the current leads the voltage, or theta v minus theta I is negative, and then the power factor is leading, or we see we have a leading power factor, and therefore the Q is negative. The Q negative means the reactive power delivered to the load is negative. So the leading power factor actually supplying the reactive power, right? Supplying the positive reactive power. But anyway, we don't have to get all the concept understood, but this is the basics we need to know. If the current lags the voltage, and if the current, let me rewrite this, if the current lags the voltage, that means theta v minus theta I, or the power factor angle, this is the phi, right? Or the phi is equal to theta v minus theta I. That's positive, and the power factor is lagging. So in that case, if the lagging, actually the power factor Q is positive, right? So for lagging power factor, we need to deliver the reactive power to the load, deliver positive reactive power to the load, to the circuit, right? And for in the actual world, in the practical world, most of the load are inductive, and the Q is positive, or we have a lagging power factor, especially if you have transformers and electric machines, stuff like that. I think that's the concept. Let's just look at an example, just see how we can calculate. Let's see, we have a P. Let's see, we have V and I, and for this example, you don't have to use the RMS. I think we should start getting used to this RMS value, right? You don't have to use RMS value to calculate P and Q. But let's see if we choose using RMS. So the VRMS is equal to 120 the VA divided by square root 2. That's 120 volts. And sometimes we just, to make sure this RMS value, we put the RMS in the unit as well to avoid any confusion. And so the IRMS is equal 10 times square root 2 divided by square root 2. That's equal to 10 amps. So these are also in RMS value. And the P is going to be equal, we need to figure out the power factor angle, right? So theta V is equal to, and remember this is in sine function, so the theta V, if in terms of cosine, we have theta V is going to be equal to negative 90 degrees, and the theta I, already this is the cosine function, so this is equal to negative 30 degrees. By the way, negative pi over 6, that's negative 30 degrees, and that's, or you can, the negative 30 is basically negative pi over 6 times 180 divided by pi, right? And so therefore the power factor angle is theta V minus theta I. That's equal to the negative 90 minus negative 30. So I get a negative 60 degrees. So if you see the so therefore phi is less than 0, and the power factor is going to be leading, right? because the current leads the voltage now, the power factor, before we do any calculation, we actually can determine this. Power factor is leading. And then we can do the calculations, and the calculation P is just equal V RMS times I RMS times the cosine phi, which is 120 times the 10 times cosine phi is negative 60 degrees. Cosine is an even function, so negative 60 degrees cosine still half, right? So we get 600, right? We got a 600. By the way, the unit for the real power or the active power is watts, and for the Q, that's equal V RMS times the I RMS times the sine phi, and that's equal 120 times 10 times the sine negative 60 degrees, and that actually is equal to negative 1039. The unit for this is volt amp reactive. So we call the vars, and the vars means the volt ampere reactive. Okay, so that's for this simple example how we calculate the real and the imaginary power. And next we're gonna look at the complex power. Okay, I'll see you in a moment.